and infinite dimensional Lie groups and Kac-Moody groups. So I really suggest you guys in the future, if you could have this as part of your library, to have it. For example, very recently in 2016, Tony C. in Santa Barbara came up with a book called Group Theory in a Nutshell. It's a book that's only a few months old, which is very useful, but you know, it's not cheap. It's about $80. But I really recommend this book in the future for you guys to have, so for here at the library. In these lectures, of course, Wikipedia is always fantastic to have. So I clipped some information from the conformal group section of Wikipedia. And here I also picked up an article that appears in the internet by this guy, which is also very useful because it has an elementary introduction to Lie algebra for physicists. But mainly I will be focused on Gilmore's book. So let me proceed. Okay, so by groups, in this case, you know, when you have a finite group, you know, by definition, it's a group that has a finite number of elements. So in this case, let's suppose that you have n elements for a group, and these elements form a group with respect to what? With respect to a multiplication, or you could call it a composition rule, or if you want to call it multiplication, you know. But rigorously speaking, it's really a composition rule. So when this set of elements is closed with respect to the multiplication, it means that whenever you have two elements, when you compose them, you will generate a third element of your group. For example, G2, the product of G1 times G2 is going to give you an element of the group. And this multiplication law is associative, meaning that the product is associative. So when you compose G with 2 and then with G3, the effect that you will get is the same as composing G2 with G3 and then composing with G1. So the product law is associative. Of course, it's very important to have an identity element, which I call E, in such a way that when you compose a group with the identity element, you can compose it in any order and you still get the same element, you know. And of course, an identity element, I mean that you have an inverse, you know, in such a way that when you compose a group with its inverse, you'll generate the identity element. Imagine you have a matrix. If the matrix has an inverse, the product rule of the product of a matrix with its inverse should give you the identity element, the identity matrix, which means you have ones along the main diagonal. This is true if the matrix has an inverse. Not all matrices have an inverse. Now, if the group is finite, it means that you have a finite number of elements, you know, and people call it the order of the group. Well, in this case, yes. 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 From the mathematical point, yeah. And the order of the group, mathematicians like to call it by this symbol, the order of the group. For example, if you look at the monster group is a finite group, and it has the number of elements is of the order of 8 times 10 to the 53. You know, that's a lot of elements. You know, that's one of the largest known group, the monster sporadic group, as they call it. And of course, the multiplication is commutative, because in reality, the multiplication might not be commutative. We know that the product of matrices is not commutative. But in the particular case, if the product law is commutative, you call this an abelian group. An example of an abelian group is the group of translations in flat space-time. The group of translations commute, so in that case it's abelian. But in general, most of the groups that we'll be working with are non-abelian, you know. Okay, so let me, you know. Okay, a Lie group, okay, I was talking about a discrete group before, which has a finite number of elements. A Lie group in reality is a continuous Lie group. So by this, I mean, imagine you have a manifold whose points are the elements of the group. So a manifold will have, in general, a continuum of points, an infinite number of points, and I guess an uncountable infinite number of points. So you can imagine those points of your manifold being the elements of the group. So this is what you really mean by a continuous group. Now, of course, it's not only enough to have a collection of points, but you have to have, when you have a Lie group, when you compose two group elements, that composition rule has to be compatible with the analytical structure of your manifold. So you have to add some more structure to it. But let me just give you an example. Let me keep going. Okay, so a Lie group is a group whose group elements are specified by one or more continuous parameters, which vary smoothly. You know, let us consider, for example, the group of rotation in 2 dimensions. You know, so the group is parameterized by the angle. You know, let's suppose that you're going to rotate, you're going to perform a rotation in 2 dimensions, and that rotation is going to be specified by the angle theta. So in 2 dimensions, you're going to have a 2 by 2 matrix, and the rotation matrix is going to be given by the entries of this matrix. Notice that when you take the terminal of this matrix, when you take you're going to have cosine square minus, you're going to have cosine square plus the sine square equals to 1. So the determinant of this matrix is equal to 1. This is what you call the special rotation group in 2 dimensions, because the determinant of the matrix is 1. And this is what people use the label a special, the SON. You have a special means the determinant equals to 1. And here you see this is a finite rotation because the angle is a finite angle. Now let's suppose that this angle were infinitesimal, an infinitesimal angle. So in that case, the Lie algebra is what is the mathematical structure that underlies the infinitesimal group structure. In this example, there is a matrix generator of the Lie algebra associated to your group. And the matrix generator is given by this matrix. You notice that this matrix, X, has an I and minus I of the diagonal. This matrix is, in this case, Hermitian. Remember what we call a Hermitian matrix? It's a matrix that, yeah. So here, when you have the Hermitian of a matrix is you take the transpose of the matrix, you flip I with minus I, and then you take the complex conjugate. So a Hermitian matrix, what you do is you do 2 things. You perform the transpose of the matrix, and then you take the complex conjugate of that. And this is what you call the Hermitian of a matrix. Now, a matrix is Hermitian in this case because you see that minus I is the complex conjugate of I. And I is the complex conjugate of minus I. Okay? So when you look at along the main diagonal, you'll see that these elements are the complex conjugates of each other. So in this case, this matrix is Hermitian. You know. Are you familiar with this, Fang? You recall what you mean by Hermitian matrix and the transpose? Yeah. Okay. So when you see a matrix like that, you look at the diagonal, and if the entries of the diagonal are complex conjugates of each other, then you know that the matrix is Hermitian. You know, that's the simplest way to see it. No. Yeah. Yes. Let me go back. Yeah, I'll go back. Yeah.
So I have a few questions.
Yeah.
So can you make it a little clear between the continuity property of the manifold and the discreteness of the group?
Yeah. Well, here I'm talking about a continuous Lie group. Imagine in this room we have 3 dimensions. We have 3 axes. So the dimension of the group is 3-dimensional. Like in this room, we have 3 axes, so it's 3 dimensions. Now, how many points do we have in this room? We have an infinity of points. Okay, so one has to be very careful. The order of the group in that case is the number of points in your manifold, which is infinite. Okay. The dimension of the group has to do with the dimension of this room, which is 3 dimensions because we have 3 axes. Okay? So
this is not an example of a discrete group.
No, it's a continuum group.
So Lie groups are not examples of discrete
No,
groups?
no, it's the continuous analog of a discrete group.
Of a discrete. So when you gave when you mentioned discrete groups, you were talking about groups, discrete groups in general.
In general.
Not particularly applicable to Lie groups.
Yes. So then I want to go from the notion of discrete group, how you jump from that notion, from the discrete to a continuum. That's what I was given. Imagine that you have a discrete set of points in this room. If you have a discrete set of points, that will be a discrete group. But if you have a continuum of points, that will be a continuous Lie group. Okay.
That's merely to mention that the configuration of the continents of the Earth is true only for now. At another time, it will be quite different. Now, to show some familiar geography, you may recognize these small islands, which taken from space, with quite configuration quite like that in the geography books. And let us do now another zoom in. In this case, let's start it zoom in on some places that we do know. Here you can see England in the rough vicinity of London. If we look more closely, we can see the Thames estuary. That is upside down. And the Thames in the vicinity of London. And then, if we look still more closely, we might see more rectangles. London are rectangles in this case. Some strange buildings, one particular domed building in something like that. Then we zoom in this strange building. Here we come back to the dominant organism in London. There are some dominant organisms now. So we have now done twice the exploration of the Earth, seeing, among other things, how very interesting it is, but also how difficult it is to look at it. Look very closely. Now, maybe I can have a globe of the Earth. All of the things that we've been talking about are on the surface of the Earth, and together globes like this one. And on this globe, there are national boundaries marked. There are photographs of the Earth from space. There are no national boundaries to be seen, which is the Earth rotates from west to east, so that the stars seem to rise east and west. And as it gets changed in this way, some parts of the Earth plunge into daylight, others plunge into night. You can imagine a wave of heat pressure which circles the Earth once every day at the terminator, the place where light and dark parts of the Earth meet. There are actually 2 such places. Talking about the morning. Well, we have so far been talking mostly about the solar system. And now our hello universe signal has gone far beyond the orbit of Mars, far beyond the Sun, but if that original hello was given us half an hour ago, the hello is just now something like how long before it reaches the nearest star? That will take another 4 years. The stars are astonishingly further away than the planets. So all we've been talking about is a cluster of little worlds around the sun, and then some immense distance to the nearest star with planets. About it. How is this discovered? How is it known how far away the stars are? We cannot bounce radar off the stars. It has to be done by some other method. And let me just give you briefly an idea of how one of the early, very clever minds in astronomy, figured out the distance to the stars. This is a man named Christianus Huygens, who lived in Holland, thank you, Bill, in the 17th century. And he argued as follows. He said, "It looks to me as if the stars are suns. The sun is near, that's why it looks so bright. If the sun were some immense distance away, it would be just a little pinpoint of light and seem very dim. How far would I have to move the sun away in order to make it as dim as some bright star at night, let's say Sirius?" So Huygens went out at night and looked at Sirius for a while. Look, look, look. Remember how bright Sirius is. Then, next day, still remembering how bright Sirius was yesterday, he went out and looked at the sun. He had a brass plate, painted black here so it doesn't shine badly to the television cameras. His was shiny. And he held the plate up to the sun and looked through each hole until he could find a hole which was so small that the amount of light from the sun which entered was just as bright as he remembered Sirius to be last night. And then he happened to know the inverse square law, which I hope many of you know, and was able then to calculate how far away you'd have to move the sun. And he came out with the answer of about half a light year. That is, it would take light about half a year to go from here to Sirius. Had Sirius, in fact, been intrinsically as bright as the sun, he would have gotten exactly the right answer. In fact, Sirius is brighter, so he got it a little bit wrong. But he came very close, within a factor of 10. And it's an astonishing achievement that Huygens did. And it suddenly made a universe vast and awesome, beyond ordinary human understanding. Many people, like Pascal, said that they were frightened. That's merely to mention that the configuration of the continents by the great spaces between the stars, because space is a mirror, is true only for now. At another time, it will be quite different. Amazingly empty. Now to show some familiar geography, I would like to close with a little discussion. You may recognize these small islands about the nearby stars. When we look out at night, picture taken from space with quite configuration, we see the constellations. Many of you have probably been fed like that in the geography books, and let us do now another forced to memorize certain patterns of dots. Zoom in this case, let's start zooming as if they were somehow firmly in places that you know. Here you can see embedded in nature, as opposed to arbitrary psychological projective tests forced on innocent children by astronomers. England in the rough vicinity of London. If you look more closely, you think so. For example, many of you know what I call the Big Dipper, and you know as, I think, the Great Bear or the Plow. Look at that. In America, we think it's a thing that you pick up liquids with, and in Britain you think it's either a bear estuary, or an agricultural implement. Now those are three quite different things. That must be merely what's in people's minds and nothing to do with what. And then still more closely, it's out there. Now what is a constellation? Constellation is a configuration. You might see more rectangulation of dim but nearby stars, bright and more London or rectangular or distant stars, which by accident